Okay, we're back for part two of solving these word problems with linear equations. We're going to get into some scenarios in this set of problems where I referenced last time that the models only make sense for small changes and they don't necessarily make sense for big changes. This first problem is going to be an okay example of that, even the first number that we're going to use is going to be a little crazy because we know that you do not grow at a linear rate. You don't always grow by a certain amount every year. But suppose that you were 24 inches long at birth and that you grow at some linear rate that we're going to call M. So I'm going to use two data points here. I'm going to say that at time equals 0, you were 24 inches. Let's do it this way. And that at time equals 10 years, you were 4 feet tall, which is 48 inches. Okay. Based on those two data points, create a linear equation. So we're going to have to find the slope. The slope is y2 minus y1 over x2 minus x1. And that's going to be 48 minus 24 over 10 minus 0 is 24 over 10 is 2.4. So my height in terms of time, I mean, you would call it length at first when the baby lies down, but you were 24 inches tall, really, if the baby could stand up when they were born, is going to be 24 plus 2.4 t. Now we're going to use that equation to estimate the height when they're 9 years old. Let's go ahead and stick that into our calculator like we talked about before. 24 plus 2.4x. Second, table settings, I'm going to set my independent variable to ask. And I'm going to go to my table here, and I want to look at when t is 9, and that's going to be about 45.6 inches. And if I want to think of that in feet, that's not quite 4 feet tall, and that makes sense based off of my model here, that it's within my range of data from 0 to 10 years old. It kind of sort of makes sense that it would fit that model, and that I might have grown a few inches, 2.6 inches in my last year. But now I'm going to try and model my height for 31 years old with this. And it says that I'd be 98.4. Let's come out and look at what 98.4 would be. 98.4 divided by 12 is over 8 feet tall. I don't think so. Not many people get to be that tall, right? So this model breaks down. So this would be 8 feet, and then 0.2 times 12. Times 12. 8 feet, 2.4 inches. I don't think so. Okay. Going to go ahead and look at the next one. Person's taking a 30-hour review course to prepare for a standardized exam, average a score of 620 on that exam. 30, 620. Person's taking a 70-hour review course. Average a score of 791. Based off of these two data points, create a linear equation for the function that describes how score varies as a function of time. So our slope is going to be 791 minus 620 over 70 minus 30. 171 over 40. $4.275. Now we don't have the initial condition this time. So I'm going to have to use one of the points that was given to me. I'll use the one with the smaller x value. And we use this form of the equation, y minus y1 equals m times x minus x1. So y minus 620 equals m times x minus 30. I'm going to go ahead and multiply those things out. And get this written in what we call slope intercept form instead of what we call point slope form. Like so. Now you don't actually make a fraction of a point on an exam like this. So that's probably actually a 492, but we won't worry about that for the sake of this model. We'll just say that this is our model here. And we have another similar equation here. Let's see, these were the same. Oh, nope, they changed this slightly now for the second problem. So they changed this to be 795. And so increases this one to this 175 over 40, changes this to, I'm just working problem number 10 now, and very few numbers are changing. But it's changing enough that I need to rework the problem a little bit. So times a negative 30. 31.25. Add 620 to that. And 488.75. Okay. So now the question is, if this is our f of x, which we might want to call it S for score or something like that, but we were asked now to find what happens when someone studies 54 hours. So 4.375 times 54 plus 488.75. And we get a score of 725. We don't have to do any rounding. They tell us to round to the 10th place, but it comes out to be an exact answer. All right, we've got two more problems in this set here. In 1995, the United States recovered 20% of its municipal solid wastes through recycling, up from 17% in 1990. So let P represent the percentage of recycled materials and T be the time. And we had in 1990, we had a percentage of 17%. And in 1995, we had a percentage of 20%. And T is going to be the number of years since 1990. So this is going to be 0 and this is going to be 5. T equals number of years since 1990. If they had not told me that, I would have let T be 1990 for my base in 1995 after that, but we're going to find our slope here. 20 minus 17 over 5 minus 0. It's going to be 3 over 5. It's going to be 0.6. Every one of these examples so far has come out to be a nice decimal equivalent for the fraction, but don't assume that that always happens. Fractions are more powerful than decimals because fractions can be written exactly all the time. Some fractions can't be written as a terminating decimal. So, and you can't enter a repeating decimal into your calculator without it being a fraction. So let's go ahead and deal with this as MT plus, this is a decrease, right? Nope, this is an increase. Yep, plus B. In 1995, it was 1990, it was 17%. There we go. I had to come back and look at my y-intercept here. When t was equal to 0, it was 17. So now we've got our function. And that was that question. It doesn't ask us to estimate anything. Now we're going to change the problem up and we are going to estimate something. So T is going to be the number of years since 1990 again. And we have 522 and we have 017. And we have a slope of y2 minus y1. X2 minus x1. 5 over 5 is 1. So there's a 1% increase every year. So this is P of T equals T, 1T plus 17. Then we need to figure out 2003 minus 1990 is 13 years. So P of 13 is equal to 13 plus 17 is equal to 30. So we would estimate that about 30% of solid wastes would be recycled in 2003. All right, that is it for this video. Come back next time and we'll graph some linear equations.